start with stability analysis in state space. Today we will see the third part, Lyapunov stability analysis, Sylvester criteria. In this we will study concept of linear and nonlinear systems, quadratic function, and third one, Sylvester criteria for definiteness of quadratic function. As we have to study Lyapunov stability criteria, but the main important thing in Lyapunov stability criteria is that this criteria is useful for both linear as well as nonlinear systems. Therefore, now we have to study what is the difference between a linear and nonlinear system. Sometimes we say that y equal to x or y equal to mx. So, this particular system is called as a linear system, but when we are saying y equal to x square, this is a nonlinear system. So, why we are saying this is linear or nonlinear? Suppose let us say you have a friend, a very good friend. In the morning he meet you. So, what will happen? He is smiling. So, morning he is smiling, but when he will meet in the evening, we will find that he is not smiling, he is just crying, he is not in good mood. So, then you are imagining why this has happened. Morning he is smiling and evening he is crying, so behavior is not good. So, that behavior is called nonlinear system. If a behavior of a person is same every time, then this is called a linear system. Now, what is the difference between this basic difference between the linear and nonlinear system? The first important point is that in linear and nonlinear system, that is homogeneity principle and superposition principle is not applicable in case of nonlinear system, whereas it is applicable in case of linear system. Just see it. Suppose I have taken a plant g of s. Now, here this is input and here is the output. Let us say the input for this plant is given as u1 of t and u2 of t, and output is y1 of t and y2 of t. So, 2 input, 2 output. Now, I am writing down the equation here like this: differentiation of dt r1 into u1 of t. So, r1 is any arbitrary constants. So, this I can write down as r1 differentiation with respect to t, that is u1 of t. And now, if you write down the equation as d of dt r1 into u1 of t plus r2 into u2 of t, similar to r1, here r1 and r2 are the arbitrary constants. So, now we can write down this as r1 into differentiation of t, that is u1 of t plus r2 differentiation of t into u of t. So, this nothing but the principle of superposition, and this part is nothing but the principle of homogeneity. So, whenever system is linear, both these superposition, which both means principle of superposition and homogeneity are applicable, whereas in nonlinear system these things are not applicable. Then you find that in linear system we are using the concept of Laplace transform. Then when the system is discrete form, then we have to use Z transform. So, all these tools are applicable in case of linear system, whereas they are not applicable, particularly Laplace transform and Z transform are not applicable in case of a nonlinear system. Then another important point is that if you see the linear system, they have only one equilibrium point. Let us say I have taken a pendulum here, this is a pendulum, this is point, this is the equilibrium point. But if you take the nonlinear system, we will find that there are different equilibrium points. Therefore, the analysis of such systems are quite difficult. Other point is that, suppose if you apply input to the linear system, let us say this is the same system. Now here some input is applied, input means let us say step input applied. Now for applying the step input, definitely we get some output. Now what happened afterward, if you change the magnitude of this input, so what happened, the system which is stable for one particular input, step input, where magnitude has some value, so slight change of the magnitude, system become unstable. That means the stability of the system, it depends upon the input as well as the initial states, whereas if you consider a linear system, the stability is depend upon the poles, or we can say the eigen value of the systems. And now the most important point which our focus is on Lyapunov stability criteria. The most important thing is that Lyapunov criteria is applicable for linear and non-linear, but as far as the what criteria you have studied earlier, particularly route criteria, root locus, Nyquist plot, they are difficult to apply for non-linear system. It is difficult, it is not possible you can say, whereas Lyapunov is applicable for the non-linear system. So in order to understand the Lyapunov's theorem, we should understand what is meant by a quadratic function. So now quadratic function, what is meant by quadratic function? Quadratic function v of x is called as quadratic function or a quadratic form when it is expressed as v of x equal to x transpose px, where p is a real symmetric matrix. P is real symmetric matrix, means the rows and columns are same. So if you take P as a matrix which is real symmetric and x transpose x like this, so what will happen? We will get a quadratic functions. So this x can be written as x1, x2 up to xn, and if you make it x transpose, it is x1, x2, xn. Now we will try to study how to formulate the quadratic equation and how we are saying that this P is real symmetric, and then how this is useful in our Lyapunov stability analysis. So for that purpose, here I am taking a third order plan, that is the order of the P I am taking as a third order. So here I am writing down v of x is a quadratic function, we can write down as x transpose px. So as I am considering a 3 state, and other words the order of the P matrix is 3, so I am writing down this equation as x transpose can be written as x1, x2, x3, and this P matrix we can write down this P matrix as P11, P12, P13, first row. And now if you see in the second row, I am writing down the elements as P12, P22, P23. This is second row, P12, P22 and P23, and you will find that the element this P12 and P12 is same, because I am considering a P as a real symmetric matrix. Now third row, P13, P23, P33, x1, x2, x3. So x4, x2, x3, this for x transpose, this x is represented by like this, and here we will find that this P13 and P13 is same, P12 and P12 is same, P23 and P23 is same. Now we solve this equation. So we can write down as and here we can write down as Now this complete row we have to multiply it with this column. So how you get P11 into x1, P12 into x2, P13 into x3. So we can write down as P11 into x1, P12 into x2 plus P13 into x3. These row column multiplications, and afterward it has been added. Now about the second row. Second row is P12 into x1 plus P22 into x2 plus P23 into x3. This second row, this column, and now third row with this column. So we can write down as P13 into x1 plus P23 into x2 plus P33 into x3. Here this matrix is 3 by 3 matrix, and what about this? This 3 cross 1. So here final matrix, it is in terms of rows and column. So we have 3 rows with 1 column. See here these 3 rows, 1, 2, 3, and this 1 column. So it is 3 cross 1. And what about this? X1, x2, x3, how many rows? 1 row and 3 columns. So we can write down as 1 cross 3. Now we again multiply this. So after multiplication, let us see what we will get. Now you to multiply this with this. So we can get it as P11 into x1 square plus P12 x1 into x2 plus P13 x1 into x3, then P12 x1 into x2, then P22 x2 square plus P23 x2 into x3 plus P13 x1 into x3, P23 x2 into x3, and lastly P33 into x3 square. See here, this we have multiplied with this, we have got these results, and now we can add the elements, and after the adding all these elements, what will get? P11 into x1 square, this one, then this P22 into x2 square, and lastly this P33 into x3 square. P11, P22 and P33 plus. So we will find that this is a P1 to x1 x2, this is P1 to x1 x2. So we will get 2 times P1 to x1 x2 plus, now this here P13, this is P13, and here also P13. So we can write down as 2 times P13 x1 into x3, and lastly P23 x2 x3, and this P23 x2 x3. So we can write down as 2 times P23 x2 into x3. So this total equation we have solved, and we have come across these particular results. And now this we are like this. From reverse thing is also possible. If you have this equation, we can write down in this form. That means here we can write down as same equation as x1 x2 x3, and about the p elements. So see here P11 P22 P33. So these element we can write down in diagonal form. So we can write down as P11 P22 P33. Now here we have P12, that is element P12 2 times. So what we can write? P12 P12. Similarly, you will find 2 times P13, So, how will write down here P13 and here P13 and then P23, that is here you will find P23 this part. So, P23 can be written as here P23 and here P23 and here x1, x2, x3. That means any quadratic function is given that can be written in this form, and particularly this P matrix, and this P matrix is a real symmetric matrix. And why this is important in Lyapunov stability? Because if we having a quadratic function, if a P matrix, then it is very easy to check the stability of the system. If the general matrix is there, it is quite difficult. That is why for Lyapunov stabilities this type of quadratic function is required. Now we solve one or two examples and we will see how to get this function. Suppose example 1, suppose we have written a quadratic function as v of x equal to x1 square plus x2 square plus 4 times x1 into x2. So, here from these equations quadratic functions there are two states. Now, what we want to write this in terms of matrix form, we want to write in terms of real symmetric matrix. So, here we can write down this as x1 x2 and now write the elements of this. So, you see the elements P11 and P22 here, the elements are 1 1, and about this x1 x2 the elements we can write down as 2 2. How to do this? Is 4, division of this is 2 2, just like here this is 2 P12. So, we have written P12 and P12. So, what are the elements are there, we have to divide by 2 and then we have to write down here. Suppose here instead of 4, let us say the element of 6, then what would have written? We have written this is as 3 and this as 3, and again here x1 x2. Now, we will take another example. Suppose this v of x equal to 4 x1 square plus 8 x2 square plus 10 x3 square plus 2 x1 x2 minus 4 x2 x3 minus 4 x1 x3. Now, this is also a quadratic function and we have to express this in terms of real symmetric matrix, that is in terms of x transpose px. So, how to write down the P? So, P can be written as here, that is here x1 x2 x3. Now, we have to write down P matrix here x1 x2 x3. So, first of all we have to write down the diagonal elements. So, which are diagonal elements? Diagonal elements means you just take the square elements, square, let us say x1 square, x2 square, x3 square. So, we write down the elements 4 8 10 in diagonal form, that is we can write down as 4 8 and 10. Now, other elements x1 x2 x2 x3 x1 x3. So, whatever value is there we have to divide by 2 and we have to write down here, that is particularly x1 x2 element is 2, divide by 2, 2 by 2 means 1. So, we can write down as 1 1. Then about this 4 x2 x3. So, divide by 2 we will get minus 2 and minus 2. So, we can write down here minus 2 and about this x1 x3 we can write down as again minus 4 minus 2 and minus 2. So, here minus 2 and minus 2, and now this is P matrix, and this is complete a quadratic function. Now, here one problem is there, this P has come. Now, from this P can we get some idea about the eigenvalues of these P matrix, in which side they are lying, whether the left side, right side. And here I am not talking about the imaginary axis, because real symmetric matrix involves the elements on the real axis, that is we will get the elements on this axis, real axis, no complex conjugate elements. Then this quadratic function, can it use for stability of the system? Now, first of all we will see how to handle these that is how to get the information about the eigenvalues of this matrix P. So, in order to get some information about the eigenvalues, not likely stability, because Sylvester, the criteria which you are developing without knowing whether it is useful for stability or not. Therefore, here only we are focusing on whether to get in which direction we are getting roots, whether on the left side or the right side. So, for that purpose in literature one criteria is there, well famous criteria, that is called Sylvester criteria, and that criteria is useful in order to determine the definiteness. Definite means whether the roots or eigenvalues on the left side, right side or at the particularly origin. To see it, Sylvester criteria for definiteness of a quadratic function. Now, consider a quadratic function as v of x equal to x transpose px. So, what Sylvester criteria say? In order that the quadratic function be positive definite, it is necessary and sufficient that the determinant of the principal minors of p, that is the magnitude, should be positive. A scalar function v of x is negative definite if minus v of x is positive definite. In this, the principal minors are calculated as leading principal minors. That is, this criteria is basically based on principal minors. That is, for example, this is a P matrix, nth order matrix. Now, we have to determine the leading principal minors. So, which are the leading principal minors in this case? So, here let us say A11, this is 1, this A11, A12, A12, A22, this is another, see here this is A11 here showing, and this is like this, and similarly we can go for another third principal minus, fourth, like this, and finally it is complete determinant. So, it has been said that if all these principal minors or the determinant of these principal minors are greater than 0, we can say that this given system matrix P is positive definite. That means, this magnitude of A11 should be greater than 0. Similarly, this magnitude, let us say we can write down as a B, this B must be greater than 0, and total matrix, the determinant of complete matrix, let us say C, we define as, let us say define as C, C must be greater than 0. So, if this is the case, then we call as a positive definite matrix. So, here V of x equals to x transpose Px is positive definite if P is non-singular and the leading principal minors of P are positive. In other words, it can say that here all the eigenvalues of P are lying on this right side of this plane, this side, then it is called positive definite matrix. Now, there is another word, positive semi-definite, same function. How to define a positive semi-definite matrix? So, in that case, whatever principal minors we calculate, if there is at least one principal minors equal to 0 and other principal minors are greater than 0, all other principal minors, then we call as positive semi-definite matrix. That is, V of x equals to x transpose Px is positive semi-definite if P is singular and the leading principal minors of P are non-negative. In other words, the eigenvalues of P, they are lying on the right side and at least one eigenvalue at this origin. If this is the case, it is called positive semi-definite. Now, the reverse case is possible in case of negative definite. So, V of x is negative definite if and only if the leading principal minors of P are negative, that is all eigenvalues of P are negative. That means, V of x is negative definite if the eigenvalues of P are lying on the left side of the S plane. Then that particular matrix P or real segment matrix P is called negative definite, and similarly V of x is negative semi-definite if and only if the leading principal minors of P are non-positive, that is at least one eigenvalues of P should be 0. It means that This particular P matrix is negative semi-definite if there are some eigenvalues on the left side of the S plane and at least one eigenvalue at the origin, then this V of x is called negative semi-definite. Now, we see one example. Consider the real symmetric matrix A as 1 1 1 1 1 1 1 1 0. Now, our aim is to check the definiteness of this matrix, whether it is positive definite, positive semi-definite, negative definite, negative significant, or in other words, that is one definition is called indefinite. Indefinite means that if there are eigenvalues on the right side, left side at the origin, then it is called indefinite matrix. There is no definiteness, only indefinite. So, see this is example. So, now you use the concept of the Sylvester criteria and you will find that this type of this criteria is given, or what I explained in most of the textbook. So, it says that in order to check the definiteness of A, we have to determine the all leading principal minors. So, for this matrix A, we start developing the leading principal minors. So, first minor is 1, see here this 1, now here it is 1, this 1 is greater than 0. Now, we go for the second principal minors. For second principal minors, we will like this 1 1 1 1, so it is 0, that is 0, and third this one 1 1 1 1 1 1 1 1 0, see this. So, this is determinant of this is 0. So, 0 0 and greater than 0. So, this is the condition of positive semi-definite. So, by means of this we have got the matrix A as positive semi-definite matrix. As the definiteness is concerned with the eigenvalues, we have seen that if this matrix is positive definite, that means that all eigenvalues must lie on the right side of the S plane. That means it must have eigenvalues either here, here, here. That means one eigenvalue should be at origin and remaining eigenvalues at the right side of the S plane. Then and then this condition is satisfied. Now, what we do? Now, we just calculate the eigenvalues of this matrix A. Now, the eigenvalues of this matrix A. The eigenvalues of matrix A are 0, 1 plus minus plus root 3 and 1 minus root 3. This matrix is indefinite. See here, by calculating the eigenvalues, this matrix coming indefinite, but actually this given matrix is positive definite. Why this has happened? By means of this approach, conventional approach, we are coming a positive semi-definite matrix, but actual eigenvalues are like this, 1 at origin, here. So, this indicate indefinite. So, this is the issue has been pointed out by K.N. Swamy. He published a paper in IIT Transaction Automatic Control, very important journal. See here, K.N. Swamy on Sylvester criteria for positive definite matrix, IIT Transaction Automatic Control 1973, and in this case he said that in order to check the positive semi-definiteness of a matrix, we have to check not leading principal minors, leading all principal minors need to be checked. That is, according to K.N. Swamy, a quadratic function is positive semi-definite if and only if all the principal minors of the system matrix are non-negative. That means, if the matrix of order n has n of p principal minors of order p, where n of p is represented by factorial p n minus p. That means, here in a given problem we have determined 3 principal minors, so they are not sufficient for checking the positive semi-definiteness of a matrix. In that case, we have to check all principal minors. Let us see, after checking the all principal minors, we are getting the result corresponding to eigenvalues or not. Now, I am writing down the matrix A, same 1 1 1 1 1 1 1 1 0. This is the matrix A as shown earlier, same matrix. Now, we have to see how many principal minors are possible here. So, according to K.N. Swamy, for third order that is n of p, where p is 3, that is 3 of 3. How many principal minors are possible? That is third order principal minors, that is factorial 3, then here 3 multiplied by factorial 0, that is 1. That is how you determine here this n of p equal to factorial n divided by pth order principal minors n minus p. So, here third order, third principal minor n of p, that is 3 of 3. So, factorial 3, 3i, factorial 3i 0i, so we will get 1, that is we will get 1 principal minors. Now, we see the second order principal minors. So, here n of p, so here 3, this is 2, here earlier we have taken 3, this is for second. So, how you get it? So, n is your factorial 3, then here pi, here is factorial 2i multiplied by here 3 minus 2, 1, factorial 1, that is 1. So, what will get 3, 2, 1, 2. So, we will get 3 principal minors, and then number of principal minors for order 1, that is here 3 n p, okay, 3 1. So, factorial 3 1, that is p is 1, and n minus p, 3 minus 1 2, this is factorial 2, again 3 2 1 2, that is 3 2 1 3 2 1 like this. So, we will get 2 cancel, we will get 3. That means, for third order the total principal minors which need to be checked are 1 plus 3 plus 3 7, whereas the conventional approach say that you have to check the 3 principal minors. Now, we will actually find out the principal minors and then we will check the determinant and we will see the result. See here the first principal minors of order 3, that is here 1 1 1 1 1 1 1 1 0. So, this is for order 3 first principal minors, and we will find that the determinant is 0, that is let us say determinant of say a, determinant of a equals to 0. Now, about the principal minors for second order. So, here we can get it as, for second we will get it at first principal minors as, for with respect to 1 here 1 1 1 0, then second we will get it as with respect to this we will get 1 1 1 0, and for with respect to this we can write at 1 1 1 1. So, if you solve it we will get 0 minus 1 equals to minus 1, here 0 minus 1 equals to minus 1, here equals to 0, that is for principal minors of order 2. And now, the principal minors of order 1, for order 1 is here this is 1, this is 1 greater than 0, then this 1 is also greater than 0, and here 0, that equals to 0. That means, here we will find that there are 0, then there are some minus 1, and here is 1 greater than 0. So, we will get principal minors, they are one at origin, other left hand side, right hand side, that means the actual value of principal minors are greater than 0, less than 0 at the origin. That means that this matrix is indefinite. Indefinite. Whereas the existing criteria says this given matrix is positive semi-definite. So, these issues has been identified by K and Swamy. Therefore, whenever we require to check positive semi-definiteness of a matrix, we have to check all the principal minors, not the leading principal minors. Now, whatever I have taught, particularly this this quadratic function, so this function will be useful in checking the stability of the system. The Lyapunov, Lyapunov is basically Lyapunov is scientist who developed this theorem. He has used this concept in checking the stability of both linear and non-linear system. These are some references: I. J. Nagrath, Gopal, D. Roy Chaudhary, and this K. N. Swamy, the paper which we are referred to. Thank you.